How's it going, guys? Today in this video, we're going to be going over Module 9.2. We're going over Module 9.2. Originally, it was Day 2, but now it's going to be Day 3. And we're going to be going over how to rewrite simple rational functions so we can actually graph them. So we're ever given a rational function, g of x equals m of x plus n all over p of x plus q, or a single degree polynomial over another single degree polynomial, we can rewrite this or rewrite the function to put it into a form that we're more familiar with. For instance, this g of x here or this g of x there, right? Those are the two g of x's we've been using in the past few videos and the past few sections to actually graph them out and to figure out a domain and range. And we can do this, we can rewrite the first g of x into these latter two g of x's by long division. So you use long division to transform a function in this form into one of the two functions underneath. Okay, sorry about the bell. And how we do this is a long division. And when we do our long division, what we're going to do is we're going to get our remainder, put that over our divisor. I don't know what's going on with the bell. I don't know why it's going off so much. But anyway, we have a remainder over our divisor, and we're going to add our quotient to it. We don't really want it in this form over here. We much prefer having a remainder over our divisor, then we're going to add our quotient to it. And we'll see in the next slide why we do that. So in example 1, we have g of x equals 3x minus 4 all divided by x minus 1. We don't really know how to graph this function by itself. We don't really know what to do with it. So what we're going to do instead is we're going to divide the top by the bottom. So you have 3x minus 4 all divided by x minus 1. So we're going to see how many times x goes into 3x, or in other words, x times what gives you 3x. In this case, it's going to be 3. 3 times x gives you 3x. So now we multiply the x minus 1 with 3. And when we do, we get 3x minus 3. 3x minus 3. And then after that, we're going to subtract the first polynomial with the second one. So 3x minus 4 minus 3x minus 3. So 3x minus 3x is 0, and then negative 4 minus negative 3 is the same thing as negative 4 plus positive 3, or negative 1. So our remainder here is negative 1. So like we said in the previous slide, we're going to write this function as our remainder over our divisor, or our remainder all over what we're dividing with. So we're dividing with x minus 1, so we have negative 1 all over x minus 1. And then we add to it our quotients. Our quotient is what is on top of the division side, right? So it's the 3. So the only problem with this function written as it is that we cannot actually have a negative 1 in the numerator. Remember, if we look at our function up here, our numerator has to only be 1. It can only really be 1. So we're going to take out that negative and put it into the front, or rather take out that negative 1. So when we take out that negative 1, we're left with 1 all over x minus 1 plus 3. And now this is in a form that we can actually graph and figure out our domain and range with. Okay? So now what we're going to do is use our new function that we found to graph and to figure out our domain and range with. So our a is negative 1. That's the number that we're multiplying the whole fraction with. Our b value is also going to be 1. Or rather, it's just going to be 1 since we're not multiplying our denominator with anything but 1. Our h is 1 since it has to be in the form x minus h. So our h is a positive 1, and our k is 3. Our vertical asymptote is x equals h. So in this problem, it's x equals 1. Our horizontal asymptote is y equals k. In this problem, y equals 3. And for our points, what we're going to do is we need to figure out what our transformation rule is. Remember, our transformation rule is bx plus h, comma, ay plus k. So we're going to take our a, b, h, and k and plug it into our transformation rule. And when we do, we end up getting x plus 1, since our b is 1 and our h is 1. And then we get negative y plus 3, since our a is negative 1 and our k is 3. So that's our transformation rule for this problem. And what we're going to do is we're going to plug in our two reference points that we always use, -1, and 1, 1 into those into the transformation rule and get our two new points that we can graph. So we plug in -1 in for x, we get -1 plus 1, which is 0. And then when we plug in -1 into -y plus 3, -1 times -1 gives you a positive 1, and then 1 plus 3 is 4. So one of our 2 points is 0, 4. And then for 1, 1, we plug in 1 for x, we get 2. And then we plug in 1 for y, -1 plus 3 is a positive 2. So our other point is 2, 2. So now we have our 2 new points, and we have our asymptotes. We can graph this function. So our vertical asymptote is x equals 1. So it'll be this line right here. And then for our horizontal asymptote, y equals 3. That's this line right there. So now we're going to put in our 2 points that we just found, 0, 4, and 2, 2. So we have our 2 our 2 points, we have our asymptotes. All we really need to do now is draw our curve that goes through that point and kind of looks like that. It runs along the asymptotes, so something like that. So that's what our graph looks like. And now we're going to figure out what our domain and range are. So remember, our domain can never equal h, right? And that's because x equals h is our asymptote. We cannot have any points on the asymptotes. So x cannot equal h. And so in this case, x cannot equal 1. So our inequality will be x is less than 1, or less than our h value, or x is greater than our h value of 1. Our set notation will be every x value such that x does not equal 1. And our interval notation will be -infinity up to 1, union 1 to positive infinity. And the reason why we use parentheses for interval notation is because x can never equal -infinity, positive infinity, or 1. So we use parentheses. For our range will be somewhat similar. Our y cannot equal k, and that's because y equals k is an asymptote, and you cannot have any points on that asymptote. So we cannot have any y values that equals k. So in this problem, y cannot equal 3. So our inequality will be y is less than our k value of 3, or y is greater than our k value of 3. Our set notation will be every y value such that y does not equal 3. And our interval notation will be -infinity to 3, union 3 to positive infinity. All right, and same thing here for interval notation. We use parentheses for everything, since y can never equal a negative infinity, positive infinity, or 3. So that's number 1. Let's go on to number 2 now. So for number 2, we have g of x equals 4x minus 7 all over -2x plus 4. So same thing as before, we don't really know how to graph this function. We don't know how to get our a, b, h, or k, or our asymptotes, or anything like that. So what we're going to do is we're going to divide the top by the bottom. So 4x minus 7, all divided by -2x plus 4. So we're going to see how many times -2x goes into 4x, or in other words, -2x times what gives you 4x. In this case, it's -2. -2 times -2x plus 4 gives us a positive 4x minus 8. And now we subtract the first polynomial with the second one. 4x minus 4x is 0, and -7 minus -8 is the same thing as -7 plus positive 8, or just a positive 1. Okay? So our remainder is 1, and we put our remainder all over our divisor, or over what we're dividing with. So we have 1 all over -2x plus 4, plus our quotient, or in this case, -2. So the only problem here is we cannot actually have a coefficient in front of our x value. If we go back a couple slides to this problem over here, we see that our standard form, or sorry, our form that we need to have it in when we have a b value is g of x equals 1 all over 1 over b times x minus h. We cannot have a coefficient in front of x. So what we're going to do is we're going to factor out that negative 2 out of that negative 2x plus 4. And when we do, we get negative 2 times x minus 2. Right? If you multiply that negative 2 back in, you get that negative 2x plus 4. And all of that minus 2. Now, this is a form that we're actually familiar with and that we can use to graph our function. So our a value, we're not multiplying anything with the whole fraction. So a is 1. Our b value will be negative 1/2. Right? Our 1 over b is negative 2, so our b will be negative 1/2. Our h is positive 2, and our k is negative 2. Our vertical asymptote, remember that's x equals h, so in this case, x equals 2. Our horizontal asymptote is y equals k, or y equals negative 2. And for our 2 points, we're going to use our transformation rule. We have bx plus h, comma ay plus k. And we're going to plug in our a, b, h, and k into that form, into that rule, and we're going to figure out our transformation rule for this problem. So our b is negative 1/2, and negative 1/2 times x is negative x all over 2. Our h value is 2, so we have a plus 2 as well. For ay plus k, our a is 1, and our k is negative 2, so we have y minus 2. So that's our transformation rule for this problem, and what we can do, or what we're supposed to do now is use our 2 reference points of negative 1, and 1, 1, and figure out our 2 new points for this function. So we plug in negative 1 for x, we get a positive 1/2, right? Negative times negative 1/2 is a positive 1/2, and add 2 to that, we get 2.5. And when y is negative 1, you plug that into y minus 2. Negative 1 minus 2 is negative 3. For 1, 1, we get negative 1/2 plus 2, that's a positive 1.5. And when our y is 1, 1 minus 2 is negative 1. Okay, so those are our 2 points. We have 2.5, negative 3, and 1.5, negative 1. So those are our 2 points. We also have our asymptotes now. So now we can graph this whole function. So let's go ahead and do that. Our vertical asymptote is x equals 2. So that'll be this line right here. And for our horizontal asymptote, y is negative 2. So we put that in as well. And for our 2 points, we have 1.5, negative 1, which will be right here, and 2.5, negative 3, which will be right there. So we draw a curve. Should look something like that. We get close to the asymptote, but we never cross it, and we go through our point that we just graphed. So that's what our function should more or less look like. That's what our vertical and horizontal asymptotes are at 2 points on both sides of the asymptotes. So now what we're going to do is we're going to figure out our domain and our range. So remember, our domain can never equal h. Since x equals h is our asymptote, we cannot have any x values on that line. So in this case, x cannot equal 2. So our inequality is x is less than 2, or x is greater than 2. Every single x value other than our h. Set notation will be x such that x does not equal 2, or every single x value other than 2. In interval notation, negative infinity to 2, the big U for union, 2 to positive infinity. Our range will be similar. It will be every y value other than k. Since y equals k is a asymptote, you cannot have any y values on that asymptote or any points on that asymptote. So y cannot equal negative 2. So our inequality will be y is less than negative 2, or y is greater than negative 2. Set notation is every y value such that y does not equal negative 2. Go to that parenthesis a little wrong. Okay? So -2 with that fancy bracket. And interval notation will be negative infinity to to -2. Then the big U for union, -2 to positive infinity. All right, so that's number 2. What I want you guys to do now is I want you guys to actually try to pause the video and try number 3 on your own. The biggest tip I can give you for number 3 is don't forget to factor out the A in the top. All right, you have to have a 1 as a numerator. So pause the video, try to do number 3, and I'll post the answer and we'll go through it in a second. Okay, so here's the answer for number 3. We have g of x equals 3x plus 8 all over x plus 2. So we don't really know how to graph that or how to do anything with it. So we're going to divide the top by the bottom. 3x plus 8 divided by x plus 2. When we do that, we end up getting 3 as our quotient, 2 as our remainder. So we end up getting 2 all over x plus 2 plus our quotient of 3. And like I said, we cannot have anything but a 1 in our numerator. So we take out that 2, since 2 over x plus 2 is the same thing as 2 times 1 over x plus 2. So we took out that 2, and now our function is 2 times 1 over x plus 2 plus 3. That's a function that we can actually graph, so that's what we have. And now we know we can figure out what our a, b, h, and k are going to be. Our a is 2, our b is going to be 1, our h is -2, and our k is 3. Our vertical asymptote is x equals h, in this case x equals -2. Our horizontal asymptote is y equals 3, since our k is 3. And if you figure out what our transformation rule is, this is what we should get right here. That's our transformation rule for this problem, x minus 2 times 2y plus 3. And when we plug in our two reference points, -1, -1, and 1, 1, we end up getting -3, 1, and -1, 5. And when we graph our function, we should get something that looks like this. And our domain is going to be every single x value other than our h, or in other words, x cannot equal -2. And that's what we get. You can look at inequality, set notation, or integral notation on your own. And range will be the same thing. Y cannot equal k, or in other words, y cannot equal +3. So you can look over the inequality, set notation, integral notation yourself. But this is what you should have done for number 3. All right, and that's the end of the video. Hopefully you guys liked it. Hopefully it helped. And that's about it.